Hi, this is Mr. Bledsoe, and in this video we're going to take a look at another one of the problems from the North Carolina Math 1 EOC, the 2016-17 released form. And there's a link to a PDF of that form below this video if you want to take a look at that. And in this video we're going to take a look at question number 6, which reads as follows. Two boys, Sean and Curtis, went for a walk. Sean began walking 20 seconds earlier than Curtis. Sean walked at a speed of 5 feet per second, and Curtis walked at a speed of 6 feet per second. For how many seconds had Sean been walking at the moment when the two boys had walked exactly the same distance? Okay, so even though the question is kind of long and wordy, this problem kind of makes a good bit of sense. I've got two people that are walking at different speeds. One's walking faster, but the one walking faster started later. So eventually the one who started later is walking faster. He's going to catch up to the slower walking one who started before. When does he catch up is basically what the question is asking. So there's a couple of things that immediately come to mind as being particularly useful for solving this problem. First thing that comes to my mind is distance equals rate times time. And this kind of formula here, the relationship between distance and rate and time, that's going to be particularly useful for coming up with some equations, an equation for Sean and an equation for Curtis. And I'm pretty sure that I'm going to be doing some kind of solving equations simultaneously in order to find out this the answer to this particular question. So this comes quickly to mind, and in fact right away, let me go ahead and write Sean walked at a speed of 5 feet per second. Sean begins walking 20 seconds earlier, so Sean begins walking first and Curtis begins walking second. Curtis is the one who's walking faster, so he's going to be catching up to Sean. So right away, since Sean starts walking like right away at the very beginning, I'm pretty sure I can write an equation for Sean, for the distance that Sean is going to be walking using this. If his rate of speed, the rate is 5 feet per second, well, rate, I remember, is kind of equivalent to the slope of a linear equation. So the distance, if the distance walked is y, and if his rate is 5, then y equals 5x is going to be the equation for Sean, in which x represents time and y represents distance. Okay, the one that looks like it may be a little bit more complicated is coming up with an equation for Curtis, because I've got this whole thing where Curtis doesn't start at the same time. In other words, Curtis doesn't really start at time 0 when Sean starts. So presumably Curtis's equation is going to be a little bit different. So I don't want to worry about that right now. And in fact, I'm going to do something that I often do, which is I'm going to start with a slightly simpler problem and then eventually move up to the more complicated one that we have here. In particular, what if, rather than having Sean start walking 20 seconds earlier than Curtis, what if they both started walking at exactly the same time? Well, if they both started walking at exactly the same time, I could draw a graph of the distance that they walked. Sean, y equals 5x, well, that's just a line with a slope of 5 and a y-intercept of 0. So this would be, for example, that would be what Sean's equation looks like, the equation for the distance that he walks. There's y equals 5x. And if Curtis started walking at exactly the same time, I know he doesn't. He starts walking 20 seconds after Sean. But if they did start walking at exactly the same time, well, this would be a graph of Curtis's line. And that would be y equals 6x. And I noticed that they're never going to, those lines are never going to intersect because Curtis is walking faster. Well, but now with this, I've got a sense of exactly what it is that I'm looking for, because if Curtis starts walking 20 seconds after Sean, Curtis starts walking second, well, Curtis doesn't start walking right here. He's going to start walking sometime later here, which means this line right here, the graph of Curtis's walking, I just want to move that line over by 20 seconds. And if I can figure out how to do that, if I can figure out how to come up with an equation for Curtis's line moved over 20 seconds, then I think I can solve this problem. So let's see what that might look like. So here's kind of the important pieces of my problem. Sean starts walking first. He's going at 5 feet per second. Curtis starts 20 seconds later at 6 feet per second. And I know that I would like to take Curtis's equation, Curtis's graph, and I would like to move it over. I want to keep the same slope, but I want to move it over by 20 seconds. And then this point right here, where the lines intersect, that's the point I'm looking for. So at this point, what a lot of students will do is they will say, well, if Curtis starts walking 20 seconds after Sean, then that just means I want to move this over by 20. Well, why don't I just say y equals, instead of y equals 6x, which is this line, how about just y equals 6x minus 20? Kind of makes sense. There's a quick way, however, to see that this is not, in fact, the correct equation for Curtis. And the way you can see that is by just doing a quick XY table and filling in a couple of values here. So one thing that I know is that when x equals 20, that is, when x equals 20 seconds, that's when Curtis first starts walking. So when x equals 20 seconds, I would expect the distance that Curtis will have walked after 20 seconds, I'm going to expect that to be 0, right? When the time gets to 20 seconds, he's only just about to start walking, so he's gone 0 feet. When the timer gets to 21 seconds, I expect that Curtis will have walked 6 feet, because he's walking 6 feet per second. Well, I can check to see if I have the correct equation just by plugging in these values for x and see if I get these values for y. If x equals 20, well, 6 times 20 is 120. 120 times 20 is 100, and that's not what I'm looking for. I want for y to be 0 when x is equal to 20. So I can tell that this is not the correct equation. In fact, some of you may remember that if you have a function, like say y equals 6x, and if you add or subtract a constant amount to that function, that does what's called a translation. It has the effect of translating or shifting the graph, not left or right, but up or down. So if I take y equals 6x and I subtract 20 from it, then that's not going to move the graph to the right by 20 units. It's going to move it down, and that's not what I want. So I begin to ask myself, well, so what exactly can I do in order to get this equation for Curtis to match up with, with the actual values that I have? Well, if you happen to know something more about translations, you might be able to figure out exactly what it is to do. There is, in fact, a way to add or subtract a number to a function in a way so as to make the graph translate to the right or to the left. Turns out that what we want to do is we want to subtract our 20 seconds. We don't want to subtract that from the whole function. We want to subtract that from just the x part. That is just the part that is related to time. Well, how do I subtract 20 from just the x part? Well, what if I write it like this? I take the original function, y equals 6x, and instead of subtracting 20 from the whole thing, what if I say y equals 6 times x minus 20? Now, how about if I take this, and if I check my numbers here and see if I get these values here. So if x equals 20, remember I want y to be equal to 0, because at 20 seconds, Curtis only just started walking, he should have gone 0 feet. Well, if I take x equals 20 and plug it in here, 20 minus 20 is 0, 6 times 0 is 0, and that one works. What about at 21 seconds, when Curtis should have walked 6 feet? Well, if x equals 21, 21 minus 20 is 1, 1 times 6 is 6, and I get that one. I can check another one if I want just to be sure. What do I get when x equals 22? That means Curtis should have walked another 6 feet. So this should be 12. 22 minus 20 is 2. 2 times 6 is 12. I'm feeling pretty good now about this equation. This is the equation for Curtis. And now I just want to find out, well, where did these two graphs intersect? That's going to be this point right here. Well, I know that they're going to intersect because Sean and Curtis have walked exactly the same distance at this point. That's this point right here, the distance. Well, since they've walked exactly the same distance is y, I can just say, well, at this time, Sean will have walked that far, 5x, and Curtis will have walked this far, 6 times x minus 20. Since those two distances are equal, I just want to know, well, what's the time value that makes those two distances equal? Now I just have an equation that I need to solve for x. 5x equals 6x minus 6 times 20 is 120. Let's see if I subtract 5x from both sides. That gives me 0 equals x minus 120. And if I add 120 to both sides, that gives me x equals 120, and that's in seconds, and that is my answer. If I want to check to see if in fact I have the correct answer, well, I know the equations for each of my two boys who are walking, Sean and Curtis. If I plug 120 into each of these two equations for x, I should get the same number because that's where they walk the same distance. So let's try it. Y equals 5x. Let's do that down here. Y equals 5 times 120. And 5 times 120, let's see, that's 0. 5 times 4, that's going to be 600. And y equals 6 times x minus 20. That's going to be 6 times, if x is 120, that's 120 minus 20. And that's 6 times 100, which is also 600. And I've just solved the problem.